Question 5. Let's see a coding solution to this. So I used this solution to be assured that I got the right answer for question 5 of the IBM Quantum Certification sample exam. So here are the necessary imports we need, and then I load my free IBM Q account using the python.env package, so I don't have to show my API key here. So, question 5. Which code fragment will produce a maximally entangled or Bell state? A maximally entangled state is a state that cannot be represented into decomposed tensor product states. So if we can decompose the state or represent it as a tensor product of 2 qubits, since we have 2 qubits here, then it is not maximally entangled. So only those states that cannot be decomposed, which means written as a tensor product of 2 states, are those states that are not maximally entangled. So that tells me that, let's think about this logically. If we had a quantum circuit here and we do operations on Q0 and operations on Q1 that are separate of each other, then they should be tensor product. We should be able to write them as a tensor product, right? Because we acted on them independently of each other. There was no correlation, no causation to have one state affect the other. And so because of that, option D is not the right answer, because it only acts on Q0. Q1 is not affected. So we can describe the state of Q1 without regard of Q0. So let's see which of the A through C is the right answer. Option A takes a Hadamard on the first qubit and then runs it through a CNOT. So we will create an equal superposition between 0 and 1 on Q0, and Q1's in the 1 state. And so then, since Q0 is sometimes in the 1 state, it will have an effect on Q1. And that already tells me there might be some entanglement happening there, since we do have an effect. The state vector form of this quantum circuit, which gets the final theoretical result of the quantum circuit in the state vector form, to see if its block spheres could be drawn. It's kind of weird. If we can draw the quantum state on the block sphere, then that means they are separable, because the only way you can draw a vector for each qubit onto separate block spheres means that they are separate and independent of each other. And here we see, wow, there is no vector here. It even shows it's not 0, it's not length 1, it's not even on here. They can't, the Qiskit library can't plot it because qubit 0 and qubit 1 are entangled, and so there is no separable form. So that's how I'm going to check each of these options to see if it's maximally entangled. And here we see that indeed the state vector form gives us amplitudes where the complex amplitude for 0, 1 and 1, 0 are the same. And that's a requirement for maximally entangled states, because there needs to be equal superposition, equal probability of measuring one and the other. So, option A is the right answer because of that. But what about B and C? Option B does a CNOT from Q0 to Q1. But since Q0 is initialized to state 0 upon execution, then the CNOT will have no effect. And so then it's essentially not going to do anything. And then the Hadamard and the X gate are acting independently of each other. So therefore, they should be able to be described as a tensor product of 2 quantum states. The final result should be up to. And indeed, we see that it is. 2 independent block vectors represent the quantum state. Option C does the same thing as option A, a Hadamard and X gate, but then it does a CZ, a controlled Z rotation from Q0 to Q1. So, and what will that give us? A maximally entangled state. Well, the Z gate on the 1 state adds a phase factor of -1 e to the I pi. And so -1 will cause a flip of the amplitude for the 1 state. But it does not cause the state to be entangled because there are still two independent state vectors that can represent the final quantum state. And therefore option C is not the right answer. And just like we expected, option D can also be written as two different quantum states. And that is also because two Hadamards create the identity and therefore invert the state back to what it was before. And yeah. So let's see what the real hardware results are. See if the quantum circuits do what we expect them to do on real quantum hardware out of this part. So getting the least busy quantum backend will hopefully run this faster than some of the more busy backends, and we can filter the list of backends that we consider by a custom function. So we say for the backend, does it have enough qubits for our quantum circuit? And is the backend a simulator? So if it's not a simulator, then we want that one, and we want it to be currently operating. So giving an array of all the quantum circuits we have means that we can run them all in one job. We don't have to wait for different jobs to execute. We give it the real hardware backend, and 1024 shots will give us enough data to meaningfully sample the probability distribution. So if we called result, that would hang around here and wait till the result's done. And if the result took an hour, you wouldn't be able to interact with this Python notebook for an hour. So if you have other code you'd rather run and work on, then I would go ahead and do that and monitor the job of your status some other way, maybe through IBM Q or through the job monitor library that Qiskit has. So then when you call result, it'll hang and we'll wait till the result's done. Then you can get the counts on those. And if you just gave it nothing, it wouldn't know what to get the counts for, since we gave it 3 different quantum circuits. And so the way to specify which quantum counts you want, you give it the circuit, which will extract the name of the circuit and return those results given the name. So here is not a very meaningful output, but we can plot them on a histogram next to each other so we can see them compared to each other. We do that giving an array of counts, and then a legend will help us identify which counts resulted from which executions, and this allows us to control the length and height of our figure. So here we see D gave us almost nearly the inverted state, almost 100%. Option B and C gave us that separable state, 1, 0 and 1, 1. And then option A gave us the maximally entangled state, almost 50% chance of measuring a 0, 1 or 1, 0. So that way we knew if we measured Q0 to be a 1, we would already know Q1 would be a 0. And vice versa, if Q0 was a 0, we would already know Q1 was a 1. That's what entanglement means. So here for a reference, I put the ket form and then the state vector form of all the Bell states. So here are the 4 Bell states. They all have this form with some NOT gates to create different versions of it. So Bell 2 has a NOT gate on the first, Bell 3 has a NOT gate on the second, Bell 4 has a NOT gate on both of them, and if we were to plot each of those on the block multivector, we would see that there's no representation. So just like this represents the Bell state that we know about, we know that A is the right answer for our question.